After looking at the Laplace transform of the basic signals, now we shall see the properties of Laplace transform. Why these properties would be of help? This would be helpful when there are complex signals or the combinations of basic signals. Okay, then we can use these properties to obtain the Laplace transform of such combinations of basic signals in a easier way. Okay, now the first property is the linearity property. Okay, which says this. That means if you have a time domain signal x of t, the Laplace transform of x of t would be x of s. If the Laplace transform of the time domain signal x of t is x of s, then the Laplace transform of sum of scaled signals. Okay, what are these a and b here? A and b are the scalars. A is associated with the signal x1 of t, b is associated with the signal x2 of t. Okay, so x1 of t, x2 of t are now scaled signals. So the whole stuff is the sum of the scaled signals. Understand that? So if you apply Laplace transform on such a signal which is sum of the scale signals, then the Laplace transform would actually be the Laplace transform being applied only on the signal, not on the scalars that are associated with the signal. So what you would do, you would take the scalars out. A and b are scalars, right? So you would take the scalars out and apply Laplace transform only on the signal. Okay, keep the scalar out, apply the Laplace transform only on the signal. Okay, so if Laplace transform of x of t is x of s, then Laplace transform of x1 of t would be x1 of s, capital X1 of s. So this is what is linear property, which says that if there is a number or a scalar associated with a signal, then while applying the Laplace transform, we separate the scalar and apply transform only on the signal, is what the linearity property telling you in vague sense. Understand that? Similarly, the second property is the time shift property. What is shift in time? See, this is time. X of t is the time domain signal. Okay, so if x of t is the signal, then x of t minus t naught is the time shifted signal. Everybody should understand this. If x of t is the time domain signal, then x of t minus t naught is the time shifted signal. Everybody understand this point? Okay, so what would be if x of s is the Laplace transform of x of t, what would be the Laplace transform of time shifted x of t? So it would be e power minus t naught s into x of s. What is this x of s? X of s is the Laplace transform of the basic signal, which is x of t here. X of t is the basic signal and that is time shifted. So you should have x of s, which is the Laplace transform of x of t, and since x of t is time shifted by minus t naught, you will have this exponential associated with the x of s. Understand that? Okay, so if we see the properties, we all know what is u of t, right? And we have derived what is the Laplace transform of this unit step function. Understand? So what is Laplace transform of this? That is 1 by s. We have derived this. So if Laplace transform of u of t is 1 by s, what is the Laplace transform of time shifted u of t? Okay, that is e power minus 2s into 1 by s. 1 by s is the Laplace transform of the basic signal, which is the basic signal here. Unit step is the basic signal, that is u of t. So that is the Laplace transform is 1 by s. So what this should be associated with, since it is shifted by minus 2, we need to associate this x of s by e power minus 2s. And so if there is minus, there should be a minus in the power here. Is everybody okay with that? Similarly, after time shift, okay, there is a shift in s domain. This is another property where what if there is a shift in s domain? What you would be doing in the time domain is what they're asking. If there is a shift in time domain, you will have an exponential in s domain. Okay, if there is a shift in s domain, you will have an exponential in time domain. This is it. Everybody's okay with this? Okay, now we shall see more such properties. Okay, so these three properties we had seen. Now we shall see more such properties so that it would help us in solving the complex problems. Complex problems means if there are combinations of basic signals, these properties would help us in getting the transforms in a easier way. Understand that? See the difference. This is time shift. This is shift in yes domain. Shift in time domain, shift in yes domain. On the right hand side, what you have is yes domain signal. On the left hand side, what you have is time domain signal. If you have shift in time, that needs to be reflected as an exponential appearing on the right hand side, that is in yes domain. If you have shift on right hand side, that is in yes domain, that needs to be reflected on the left hand side in time domain. But see the difference in the powers of exponential. If it is minus s naught on the right hand side, it would be plus s naught in the power. If it is minus 2 in left hand side, that is time domain, it would be minus 2. The same would reflect here. But if it is minus, it would get plus in time domain. So just observe the difference in the exponentials that get associated with the signals in respective domains. Fine. Now the fourth property that we need to look at is time scaling. Everybody just take down this. What we are looking at is time scaling property. How does this time scaling property looks like? Everybody just see here. What is scaling? Suppose see here, if x of t is a signal, okay, so having a scalar here is amplitude scaling. Everybody understand that? This is amplitude scaling. Amplitude scale. Yeah, this is amplitude scaling. Fine. Now, if you have signal x of t, but this t is being scaled, what is this? This is time scaling. There are two types of scalings. Understand that? One is amplitude scaling and other one is time scaling. Where did we see this amplitude scaling? Multiplying by a scalar. Where did we see in see here in linearity property? The signal is being scaled by the scalars here, right? Multiplied by a scalar, that is amplitude of x1 of t is being scaled. Here by attaching b here along with this, it is as good as varying the amplitude of x2 of t. So amplitude of x2 of t is being scaled. So these two are amplitude scales. A and B are amplitude scaling. Okay. So this is A being multiplied to x of t is you're multiplying A to the signal x of t. So it is amplitude of the x of t is being scaled. So that's why it is amplitude scaling. Whereas here what's happening, it's you're not multiplying A to the signal x of t, but you're multiplying A to the time t. So that's why it is time scaling. So you need to make out the difference where you are multiplying your A. If you multiply A to the signal, it is amplitude scaling. If you multiply A to the time, it is time scaling. Understand? So if you scale the time, okay, what would be the Laplace transform of the scale time scale signal is what we need to look at. See, if Laplace transform of x of t is x of s, then Laplace transform of the time scale signal, what is that? X of at is the time scale signal. What is the Laplace transform of time scale signal is what they're asking. What is it? So if you have time scale, then the Laplace transform would look like this: 1 by a times x of s by a. This is how it is going to look like. Everybody understand that? If you have x of t, it is x of s. If you have x of at, then on s domain, here you have 1 by a, that is 1 by the scalar a, okay, into the Laplace transform of the basic signal, wherein s is being replaced by s by a. See, s is being replaced by s by a. So this is time scaling property. That is the fourth one. We'll be solving the problems on it, then you will understand when all this would be of help. Okay. Now, the fifth property we shall see now. Everybody take down the fifth property. Fifth property is time differentiation. Okay. It is time differentiation. Everybody take down this. So how does it look like? See here. If x of t has got the Laplace transform which looks like x of s, then okay, time differentiation, that means you need to have differentiation on the time domain, not on the Laplace domain. Okay, so time differentiation means, see here, dx of t by dt. This is time differentiation of the time domain signal with respect to t. How should this look like is the question that is being asked. So the Laplace transform of the time differentiated signal would be s into x of s minus x of 0. So you need to be a little careful here. On the s domain, you have sx of s. S is x of s is the Laplace transform of x of t, that needs to be multiplied by s minus x of t, where t is being replaced by 0. So this is time domain signal evaluated at t equal to 0. Understand, this is capital X, this is small x. So you need to be very particular about the notations that are being used when we are representing the time domain signal and Laplace domain or S domain signal. Everybody understand? Now this is first order differential. What if you have nth order differential? See here? See here, this is note. Okay. So what can happen is I've given you the first order differential note, okay, for nth order differential. How does it look like is what I'm giving you. So the nth order differential means here it is first order because you have power of 1, right? This and this here. So this is first order differential. How does the second order differential looks like? Okay, it looks like what? D to the power n x of t divided by what? D t power n. So if you have an nth order differential like this, okay, the Laplace transform of this would be s power n x of s minus s power n minus 1 x of 0. Okay, just go on and on and on. Okay, minus x power n minus 1 of 0. So this is how the things go. So if you have nth order differential. So can you write the second order differential Laplace transform? Can you write the second order differential Laplace transform? Can you do that now? If you have second order, how the Laplace transform of a second order differential is going to look like? For example, if your first order, what we have shown you, example, the Laplace transform of d square x of t by dt square. What would be the Laplace transform of this? Okay, so it is nth order. For nth order it is this. For second order it is supposed to be s square capital X of s minus, okay, s to the power n minus, what is n? N is 2, right? So s to the power 2 minus 1, so it is s, okay, x of 0, it's throughout minus, okay, minus, what you would have, what is this, what is this going to be? 2 minus 1, it is saying, right? 2 minus 1, what does that mean? What does that mean? It means that you have x dash 0. So x to the power 2 minus 1 of 0. What is this? These are all boundary conditions. This would be given x of 0 minus x dash of 0. X dash of 0 would be given in the problem. Understand that? Okay. So x of 0 is understood. X of 0 is, if you have x of t, replace t by 0 in x of t, will get x of 0. But what is x dash of 0? It is some boundary condition. There's some condition which would be given when you are obtaining the Laplace transform of the second order differential. Everybody understand that? So would be given. This would be given in the problem when you're asked to find out the second order differential of a signal. Understand? So they are called as initial conditions. They are called as initial conditions. Fine. So it would be given to you, not to worry. So this is what we are supposed to be doing if we are asked to find out the Laplace transform of a time differentiate signal. That differentiation could be first order differential or the second order differential or the third order differential. This is how the things go. Everybody understand this? Now let's go with the sixth property, that is integration in time domain. Everybody take down this. The sixth property is, we have seen differentiation in time domain. Now we shall see the integration in time domain. Integration in time domain. So if you differentiate in time domain, what would be the Laplace transform of that? If you integrate in S domain, what would be the Laplace transform of that? Is what we are going to look at. Fine. Now, everybody see this. Similarly, as we have done for the other properties, let's again write. If x of t has the Laplace transform x of s, then the time integration in time domain, right? So that means we need to integrate the time domain signal. How to integrate? 0 to t x of t dt. So if you have the integrated signal, time integrated signal, then the Laplace transform of such an integrated signal, okay, would be given as x of s divided by s. Everybody understand this point? So if you have the integral of a signal, okay, the Laplace transform of integral of a signal is Laplace transform of the signal divided by s. Fine. So this is the integration in time domain property. So let's take down the seventh one, that is differentiation in, everybody just copy down this, differentiation in S domain. This is another property. We have seen differentiation, but that differentiation was differentiation in time domain. Let me show you that. Here, this is differentiation in time domain, where the time domain signal is being differentiated. Okay, that is what is called time differentiation. Now this is differentiation in S domain. S domain differentiation. Okay, so how does that look like is what we are looking at. Fine. See here now. If you have x of t, and if the Laplace transform of x of t is x of s, then Laplace transform of tx of t, I'll be talking about this. The Laplace transform of tx of t would look like would look like what? Mm, minus d by ds of x of s. So this is how it is going to look like. Understand this, everybody? So that means if you are differentiating a signal in S domain, then it is as good as multiplying t to the time domain signal and having a negative sign to the differential we have in S domain. Okay, so this needs to be derived. Okay, but we have not derived it in the class now. Okay, because all the derivations are dealt in detail in the textbooks prescribed. Okay, so we'll be looking into that if you want derivations of that, which are important from examination point of view. Okay, but here, since the time is short, okay, we're not getting into the derivation part. Is everybody okay with that? Okay, so this is what is going to happen if you differentiate a S domain signal. That is x of s. If you differentiate with respect to s, then on the time domain you will have t being multiplied to the time domain signal x of t, and in S domain you will have a negative sign accompanying the differential. Is everybody okay with that? Suppose note you take, what if you have t to the power n? What if you have t to the power n? That is, in general, the Laplace transform of t to the power n x of t, if you have, how is that going to look like? See here, this would be equal to minus 1 to the power n. What power you have to this t needs to be given to this minus 1. So minus 1 to the power n, okay, and the same power would go to the differential. The order of the power would also change. Order of the differential would also change accordingly. Understand that? Okay. So example, if you have example, what is Laplace transform of t square x of t is the question. What would this be? This would be minus 1 to the power 2. Okay. Then into, sorry. Okay. Into this second order derivative differential of x of s with respect to s. So that means if you have even numbered power, it would just be this. So this would be positive. This minus 1 would not come into picture. If it is even powered, if it is an even power of t, then t squared to the power t to the power 4, t to the power 6. For all those, this minus 1 would not exist, because minus 1 to the power to the even power, okay, would always be 1. So this is how the differentiation in S domain would look like. Okay, or instead of calling it as differentiation in S domain, multiplication of t to x of t you can call, but Since we have a differential in S domain, it would be easier for us to remember. But when you're dealing with differential with S domain, you have to attach a minus sign if t to the power 1 is there. Okay, so this is what one should understand. Okay, take down the eighth property. There are too many properties. We are ending with the 8 properties because this is what is going to be helpful for solving the problems. Okay, so we shall end with the 8th property, that is convolution. Convolution property. This convolution is something that you'll be learning in detail with detail in signals and systems in 4th semester, that is next semester. Okay, but this property deals with the convolution of the signal. Understand, convolution of the signal is some mathematical operation which is tedious to perform. Okay, convolution is a mathematical operation. Everybody just see this. Convolution is a mathematical operation which is tedious to perform, which is, let's try, difficult to perform. Everybody understand this. Okay, convolution is a property. Okay, it's a mathematical operation which is difficult to perform. Fine. So this difficult operation can be done easily if you transform. Everybody understand this? Okay. Suppose you have, since it is a mathematical operation, you need two operands. Two operands. Okay. So let's say this is the node. Okay. This is just a node. Okay. Convolution property tells us what? See here, the statement of convolution property. Convolution property tells us that, okay, the what? Convolution of the signal, convolution of time domain signals is multiplication in what? Laplace domain. This is what is the meaning of it. So what is convolution? See here, if you have x of t, we obtain what? That is, if you have x of t, we obtain the Laplace transform as x of s. Okay, suppose you have two signals here, x1 of t and x2 of t, and these two signals are being convolved. This is convolution operator. Understand that? So this is convolution operator. Let me write that. Convolution operator. So this is convolution operator. Let's write. Okay, so these two signals are being convolved in time domain. So if you have such two signals which are being convolved, okay, then what happens in the Laplace domain? X1 of t is x1 of s, x2 of t is x2 of s in s domain. Okay, so it is simple multiplication. What is this? Multiplication of signals. That means if it is convolution of signals in time domain, then by applying Laplace transform, what we can do, we can try to transform this convolution operator into multiplication operator in Laplace domain. Is this okay with you, everybody? So how many properties we have seen now? We have seen 8 properties. Okay, now we shall solve problems by using these 8 properties. Is everybody okay with this?